Very good morning to you. Introduction to Geochemistry, Lecture 1. Coming to the outline of the topic, this includes Introduction to Geochemistry, Tasks of Geochemistry, Historical Review, Subdisciplines of Geochemistry, Challenges in Modern Geochemistry, Emerging Trends in Geochemistry, Significance of Geochemistry, Earth in relation to Universe, Nature and Composition of the Universe, the nature of the solar system, composition of the Sun, sunspots and auroras. Coming to the introduction, geochemistry may be defined as the science which is concerned with the chemistry of the earth as a whole and of its component parts. Geochemistry is the study of the earth's chemical composition and the chemical processes that shape it both in the past and the present. It uses chemical principles to understand the origin, evolution, and distribution of elements within the earth's various systems such as mantle, crust, oceans, and atmosphere. Geochemistry, it deals with the distribution and migration of chemical elements within the earth in space and time. Geochemistry plays a crucial role in understanding various geological processes, including mantle convection, planetary formation, and the origin of the mineral deposits. Geochemistry investigates the chemical makeup of natural materials like rocks, minerals, water, soil, and even biological tissues. The science of the occurrence and distribution of elements in the universe as a whole is called cosmochemistry. Cosmochemistry is a branch of the science that focuses on the chemical composition of celestial bodies such as planets, moons, asteroids, and comets. It seeks to understand the origin and evolution of these bodies by studying the elements and compounds that make up their composition. Cosmochemists, they analyze samples from the extraterrestrial sources like meteorites to gain insights into processes that have shaped the universe over billions of years. What is geochemistry? So, the study of the chemical composition of the earth and its rocks and minerals. The urge to make the geology more quantitative, it has led to the widespread inclusion of the so-called basic sciences, such as the physics and chemistry, into the study of the geology. The term geochemistry, it was first used by the Swiss chemist Schwanbein in 1838. Geochemistry, it can be broadly defined as the science concerned with all the geological studies involving chemical change, and it includes the study of the distribution of elements in minerals, rocks, and soils, along with the interaction between these earth materials. V.M. Goldschmidt, who is regarded as the founder of the modern geochemistry, characterized geochemistry in 1933 with the following words. Geochemistry can be broadly defined as the science concerned with all the geological studies involving chemical change. This was defined by Clark, and it includes the study of the distribution of elements in minerals, rocks, and soils, along with the interaction between these earth materials. Then coming to the what are the tasks of geochemistry? Geochemistry, it encompasses a broad range of tasks related to understanding the Earth's chemical composition, processes, and evolution. The major task of geochemistry is to investigate the composition of the Earth as a whole and of its various components and to uncover the laws that control the distribution of various elements. Geochemists conduct field studies, laboratory analysis, and data interpretation to investigate the distribution of chemical elements in various Earth systems, including rocks, minerals, and soils, water, and atmosphere. Geochemist, it needs a comprehensive collection of analytical data of the terrestrial mineral, that means rocks, waters, and atmosphere, and the uses analysis of meteorites, astrophysical data about the composition of the other cosmic bodies, and geophysical data about the nature of the Earth's inside. Much useful information, it also came from the synthesis of minerals in the lab and from the observation of their mode of formation and stability conditions. These models, they are helpful to predict the movement of elements and to assess the environmental impacts and explore further natural resources. What are the main tasks of the geochemistry? So we can say that the number one task or the important task is the determination of the relative and absolute abundances of elements and of the atomic species, which are also known as isotopes in the Earth. Relative abundance. What is the term relative abundance? Relative abundance, it refers to the percentage of each element or atomic species present in a sample compared to the other elements or species in the same sample. While the absolute abundance, it refers to the total amount of a specific element or species in a sample regardless of other elements. Coming to the next task of geochemistry, the study of the distribution and migration of individual elements in various parts of the earth like atmosphere, hydrosphere, the crust, etc. and in minerals and rocks with the object of discovering principles which govern the distribution and migration of elements. It focuses on understanding the relative and absolute abundances of chemical elements in various components, including the atmosphere, hydrosphere, and the crust. And geochemistry, it helps in the understanding the Earth's history, composition, and processes. It also deals with the migration and cycling, geochemical maps, mineral chemistry, isotope geochemistry, understanding ore deposits, studying Earth's interior, tracing pollution sources, etc. The other tasks of geochemistry, it includes field studies and planning. This includes collecting the samples. Geochemists, they collect the samples of rocks, minerals, soil, water, and sometimes air to analyze their chemical composition. And this also includes mapping geochemical areas. They may also create the maps for geochemical features to understand the distribution of elements in a particular region. And this also includes planning sampling programs. Geochemists design sampling strategies to effectively capture the information about the particular target area. It also includes laboratory analysis, like analyzing the samples. Geochemists, they conduct various analytical techniques to determine the chemical composition of samples, including elemental and isotopic analysis as well. Working with the specialized equipment, geochemists utilized advanced equipments like spectrophotometers and mass spectrometers to analyze samples. It also includes data interpretation. They interpret the data from analytical tests to understand the chemical processes and relationship within the Earth systems. The other task of geochemistry is modeling and research. So developing geochemical models. So these models, they are helpful to identify various Earth system processes, and geochemists, they create models to simulate the behavior of chemical elements in the Earth systems and predict their movement. This also includes environmental assessment. Geochemists assess the impact of human activities on the environment by studying the distribution and behavior of contaminants or pollutants in different media. And this also includes resource exploration. Geochemists analyze the chemical composition of rocks and minerals to identify potential deposits of valuable or economic resources. And this also includes scientific research. Geochemists conduct research to advance our understanding of Earth's chemical processes and its evolution. And this also includes the other tasks like report preparation. Geochemists prepare detailed reports and scientific papers based on the research findings. These are the other tasks of the geochemistry. Coming to the historical review. The term geochemistry or the name geochemistry, it was first introduced by Schwanben since more than 160 years. The term geochemistry was coined by Christian Friedrich Schwanben in 1838. Schwanben is a German-Swiss chemist who was known for discovering ozone, and his writing on the subject introduced the idea of a comparative geochemistry to understand the origin of planets and their inorganic matter. Clark, he was a chief chemist of the US Geological Survey from 1884 to 1925 and has contributed very much to the science geochemistry. F.W. Clark's significant contribution to geochemistry was the collection, classification, and synthesis of data on the chemical composition of rocks, minerals, and waters, which he published in his book, The Data of Geochemistry. This book became a foundational work for the field, helping to establish the science of geochemistry and providing a comprehensive overview of the chemical elements in the Earth's crust. Clark number, it is very famous. Clark number or Clark is the relative abundance of a chemical element, typically in Earth's crust. And the technical definition of the Earth's crust, it varies among authors, and the actual numbers also vary significantly. William Goldschmidt, 1888 to 1947, he has contributed significantly to the roles of the ionic size, coordination, and atomic substitution in crystal lattices. Victor Goldschmidt, he often considered as the father of modern geochemistry. He made significant contributions by classifying elements, establishing biogeochemistry, and promoting research into the geochemistry of the hydrosphere and marine environments. His work revolutionized our understanding of the distribution of elements in the Earth's crust and deep interior. The contributions of the USSR geochemists are remarkable, especially after the improvement of the analytical techniques. Coming to the subdisciplines of geochemistry. So this includes atmospheric geochemistry, cosmochemistry, trace element geochemistry, isotope geochemistry, petrochemistry, soil geochemistry, sediment geochemistry, marine geochemistry, biogeochemistry, planetary geochemistry, geochemical thermodynamics and kinetics, aquatic chemistry, organic geochemistry, environmental geochemistry. What is atmospheric geochemistry? Atmospheric geochemistry, it studies the chemical composition and reactions within the Earth's atmosphere, including natural processes and human influences. It examines the distribution, behavior, and fate of various chemical elements and compounds in the air, as well as how they interact with the other Earth systems like the oceans and land. This field, it is crucial. Atmospheric geochemistry is crucial for understanding climate change, air quality, and the evolution of the Earth's atmosphere. Coming to the cosmochemistry. What is cosmochemistry? Cosmochemistry is the study of the chemical composition of the universe, especially focusing on the solar system. It investigates the formation and evolution of chemical elements, including nucleosynthesis processes, and explores the processes and shaped the materials in our solar system. Then coming to trace element geochemistry. What is this trace element geochemistry? Trace element geochemistry, it studies the distribution and migration and behavior of trace elements in geological materials, helping to understand the Earth's formation, evolution, and processes. Trace elements present in very low concentrations, less than 0.1% by weight, are crucial for deciphering geological history, rock types, and the origin of the magmas. Next, coming to isotope geochemistry. What is this isotope geochemistry? Isotope geochemistry, it studies the variations in the isotopic composition of the elements in the Earth and other celestial bodies. It's broadly divided into radiogenic and stable isotope geochemistry, each offering insights into different aspects of geological processes and Earth's history. Petrochemistry. Petrochemistry is a field of the chemistry focused on chemical composition, properties, and transformations of petroleum and natural gas and the production of petrochemicals from the resources. Soil geochemistry. Soil geochemistry, it involves studying the chemical composition of soils, including the distribution and abundances of various elements and compounds. This field is crucial for understanding soil processes, assessing soil quality, and identifying potential environmental hazards. Sediment geochemistry. Sediment geochemistry, it studies the chemical composition of sediments, analyzing elements, isotopes, minerals, and compounds to understand their origin, depositional environments, and past conditions. This field, it helps decipher provenance, climate variations, tectonic settings, and reservoir characteristics using various analytical techniques like mass spectroscopy and mineral analysis. Coming to marine geochemistry. Marine geochemistry is the study of the chemical composition and processes within the ocean, including seawater, sediments, and biota. It's a multidisciplinary field that combines chemistry, geology, and oceanography to understand how the ocean interacts with the atmosphere, the solid earth, and the living organisms. Coming to biogeochemistry. Biogeochemistry, it studies the interactions between the living world, that is the biosphere, and the physical environment, including atmosphere, hydrosphere, and lithosphere. Planetary geochemistry, it studies the chemical composition and processes of planetary bodies, including Earth and the other planets, to understand their formation, evolution, and interactions. Coming to geochemical thermodynamics and kinetics, this studies the energy transformations in chemical processes within the Earth systems, focusing on the equilibrium states, disequilibrium, and the role of chemical reactions in achieving stability. Coming to the aquatic chemistry. Aquatic chemistry is the study of the chemical processes and interactions within the water bodies, including natural water systems like lakes, rivers, oceans, as well as engineered systems like wastewater treatment plants. Organic geochemistry is the study of the chemical composition and behavior of organic matter in the Earth's crust, including the formation and transformation of fossil fuels. Environmental geochemistry, it studies the movement, distribution, and fate of chemical elements within the Earth's surface systems, particularly focusing on how these processes affect human and environmental health. Coming to challenges in modern geochemistry. Modern geochemistry, it faces numerous challenges in understanding Earth's complex systems. One major challenge is the sheer complexity of the Earth materials. Pollution from industrial activities, mining, and agriculture, it can have far-reaching effects on the environment. Another challenge is the impact of human activities on the Earth system. Geochemists play a crucial role in assessing pollution levels, identifying sources of contamination, and developing strategies for remediation. Climate change is another major challenge that geochemists are addressing. By studying the past climate changes recorded in rocks and sediments, geochemists they can gain insights into the causes and consequences of climate change. Coming to the emerging trends in geochemistry. The field of geochemistry is constantly evolving with new trends and innovations emerging all the time. One emerging trend is the use of advanced analytical techniques such as high resolution mass spectrometry and synchrotron radiation spectroscopy. So these techniques allow geochemists to analyze samples with unprecedented precision and sensitivity or accuracy, opening up new possibilities for understanding Earth's systems. Another emerging trend it is the use of the big data and machine learning. By analyzing large data sets, geochemists can identify patterns and trends that would be difficult to detect using traditional methods. And geochemistry it encompasses a wide range of subfields, each focusing on different aspects of Earth systems. And environmental geochemistry, for example, it studies the impact of human activities on the Earth's environment. What is the anthropogenic nature, how the pollutants are released into the atmosphere and then the ecosystem. And it involves analyzing soil and water samples to assess the pollution levels and to identify the sources of contamination. Coming to the significance of geochemistry, how the career will be. A career in geochemistry, it offers a wide range of opportunities in both academia and industry. In academia, geochemists they can work as professors or researchers at universities and research institutions. They can conduct cutting-edge research, teach courses in geology or environmental science, and mentor students. Geochemists they can work in fields such as mineral exploration, environmental consulting, and resource management. They use their knowledge of the earth materials to identify potential mineral deposits and develop strategies for extraction. In environmental consulting, they assess the pollution levels and develop strategies for remediation. In resource management, they evaluate the economic potential of natural resources and develop sustainable extraction methods. Good analytical and problem solving skills are very essential, and geochemistry plays a crucial role in evaluating the economic potential of natural resources. Good analytical and problem solving skills are also essential as geochemists often work with complex data sets and they must be able to interpret their findings. Geochemistry plays a crucial role in evaluating the economic potential of natural resources. By analyzing the chemical composition of rocks and minerals, Geochemists can identify potential mineral deposits and assess their economic viability. This information is crucial for guiding mineral exploration and resource management. It also helps scientists understand the behavior of elements in natural systems, which is important for developing sustainable extraction methods. By studying the movement of the elements through Earth's systems, geochemists can assess the environmental impact of mining activities and develop strategies for minimizing pollution and waste. Coming to the nature of the universe. The nature of the universe, it encompasses all of space-time and its contents, including energy, matter, and the physical laws that govern them. It's often described as the totality of existence, encompassing the everything that has been, is, and will be. The universe is expanding entity, approximately 15 billion years old, and consists of both visible and invisible matter and energy, with the latter making up a significant portion of its substance. The origin of the universe, it is explained by Big Bang theory. The Earth as a unity within the solar system, which consists of the sun, the planets and their satellites, the asteroids, the comets and the meteorites. Sun is the only star within our galaxy. Probably it contains more than 10 to the power of 11 stars with a diameter of about 70,000 light years. And the universe is not static, it is expanding. And at large scales, everything is moving away from everything else. The universe appears smooth and similar in all directions, a property known as the cosmological principle. The universe is composed of various forms of matter and energy, including ordinary matter, and dark energy. Coming to the origin of the universe, the prevailing scientific theory is that the universe began with the Big Bang, a rapid expansion from an extremely hot and dense state. So the origin of the universe is explained by Big Bang theory, which suggests that the universe began from a tiny, hot, dense point that rapidly expanded and cooled. This expansion, it continues today as evidenced by the National Geographic Science article and studies of distant galaxies. The Big Bang theory, while not explaining the very beginning, it describes the subsequent development of the universe, including the formation of atoms, stars, and galaxies. The universe contains a vast array of the structures, including galaxies, galaxy clusters, and superclusters. Galaxies means vast collection of stars, gas, and dust held together by gravity. And galaxy clusters, it includes groups of galaxies bound together by gravity. And superclusters, these are the largest known structures in the universe, consisting of multiple galaxy clusters. Coming to the age of the universe, so these are the table giving the natural radioactive series of significance for geological dating. The parent elements, that is uranium-238, and its half-life is 4.5 into 10 to the power of 9 years, and the end products are the emission of the uranium. It gives rise to lead-206 and 8 helium particles. And coming to uranium-235, the half-life of uranium-235 is 7.1 into 10 to the power of 8 years, and the end products are lead-207 and 7 helium particles. And thorium-232, half-life is 1.4 into 10 to the power of 10 years, and the end products are lead-208 and 6 helium particles. And rubidium-87, the total half-life is 4.9 into 10 to the power of 10 years, with the end product of strontium-87. And potassium-40, having a half-life of 1.3 into 10 to the power of 9 years, the end products are argon-40 and calcium-40. Coming to the nature of the solar system. The solar system is a gravitationally bound system. It consisting of the sun and all the objects that orbit it, including planets, dwarf planets, asteroids, comets, and interstellar gas and dust. It is formed about 4.5 billion years ago from the collapse of a cloud of gas and dust called a solar nebula. The sun, a star, occupies the center of the system, and the planets, moons, and the other objects orbit around it. The study of the geochemistry, the solar system, it is of primary importance, and this is of insignificant in relation to the universe as a whole. The sun contains over 99.9% mass of the system, but it only consists of 2% of the angular momentum. The planets all revolve in the same direction around the sun in elliptical orbits, and these orbits all lie in practically one plane. The planets themselves, they rotate in about their axis in the same direction as their direction of revolution around the sun, except Uranus and Venus, which they have retrograde motion, and most of the satellites also revolve in the same direction. The planets show a regular spacing as expressed by Bode's law, and they form two contrasted groups like inner group and the outer group. The inner group of small planets like Mercury, Venus, Earth and Mars, these are also called as the terrestrial planets, and an outer group of large planets known as Jupiter, Saturn, Uranus and Neptune, these are called as major planets. The major part of the angular momentum of the solar system is concentrated within the planets, not in the sun, in spite of the concentration of mass in the sun. This is about the data on the solar system. Coming to the composition of the universe. The universe is primarily composed of dark energy, that is 68%, and dark matter 27%, and ordinary matter 5%. Ordinary matter, this is also known as the baryonic matter. It includes all the things that we can see and interact with, like stars, planets, and people. Dark matter and dark energy are mysterious substances that have a significant impact on the structure and evolution of the universe, but their nature is still not fully understood. So the composition of the universe as obtained by the spectroscopic examination of solar and stellar radiation, and also by the analysis of the meteorites. And helium, it was first discovered in the sun spectrum by Lockyer in 1868, and this was identified on the Earth by Ramsay in 1895 as the gas has evolved when uraninite was heated with a mineral acid. And technetium, it is an element which is not detected on the Earth because of its short half-life, and it has been seen in some stellar spectra due to its recent synthesis in these stars. Coming to the sun. Sun is the biggest, brightest and hottest object in the solar system. The sun is an ordinary star, and the sun, it is made up of 70% hydrogen and 28% helium. This helium was discovered in the sun's chromosphere in 1868. Coming to the composition of the sun. Structure of the sun, it consists of four parts, like the visible surface is also known as photosphere, and the solar interior, two layers of atmosphere known as the chromosphere and corona. Sun's interior, it is not visible for observation, and the photosphere, it is the bright disk, and it is the layer that radiates most of the sunlight. The absorption spectrum of the sun, it shows that about 90% of the atoms present on the sun's surface is of hydrogen and 10% is helium. The chromosphere is above the photosphere, which is a layer of hot incandescent gases, and helium was discovered in the sun's chromosphere in 1868. The photosphere, it is a bright disk, and it is the layer that radiates most of the sunlight. And the chromosphere is above the photosphere, and it is a layer of hot incandescent gases. And the corona is the outermost part of the solar atmosphere. At the outer edge of the corona, ionized gases escape the gravitational pull of the sun, and the streams of protons and electrons from the corona constitute the solar winds. Coming to sunspots and auroras. Sunspots are temporary, cooler, dark spots on the sun's surface, specifically the photosphere. They are caused by strong magnetic fields that inhibit heat from reaching the surface. Sunspots are dark blemishes on the sun surface, and the black center of a sunspot is known as umbra, which is surrounded by a lighter region known as penumbra. Sunspots are a key indicator of solar activity, and their number varies over an approximate 11-year solar cycle. Sunspots typically stretch 1,000 to 1 lakh miles across. Sunspots are cooler than other areas on the sun, making them appear darker. Solar gases are explosive events associated with sunspots. Coming to auroras. Auroras, these are the ejected particles of the sun that reach the surface, Earth's surface, and disturb the ionosphere. Auroras, also known as northern and southern lights. Northern light is known as aurora borealis, and southern light known as aurora australis. And these are the natural light displays in the Earth's sky primarily observed near the poles. These displays are caused by the interaction of charged particles from the Sun with the Earth's magnetic field and atmosphere. So during the ejected events, that is the auroras events, the magnetic poles of the upper atmosphere, they are set aglow for several nights, and the spectacular effects, these are altogether known as auroras. And the source of energy in the Sun is the nuclear fusion. Hope you have followed the content. See you in the next video. Thank you for your time.